Hello and welcome back to Tomography. Back in my backyard again. Maybe I'll make this a thing. The sun's about to come up over that house, so I think my lighting's about to be screwed up. Anyway, so let's talk about what we've done so far. So last time we started looking at the Fourier transform of periodic functions, and in doing so, that allowed us to prove this theorem that we called the Nyquist sampling theorem. The Nyquist sampling theorem basically told us that if we sample a function at a, say, countable number of places, then we can use the sinc function to interpolate the function back. But better than just any sort of interpolation like you do with, say, polynomial interpolation or other things like that, if our function ended up being band limited, then it gave us an exact reproduction of the function itself. So that tells us that we can replace, for band limited functions, we can go ahead and replace the actual function value at a continuum of points with just a countable number of samples. Other things that we know is that we can take we can take the sinc function and in the limit it actually decays like 1 over x or so, provided that our sequence is also decreasing, we can guarantee that that we're going to get an improved approximation using more and more points. But we can, if we just fix some sort of error bound, we can just go ahead and we get an approximation out of it. And we can make that approximation as good as we want, but 1 over x isn't actually the best decreasing rate, and there's probably some better ways to do it, but for now we won't worry about that. There comes the sun. Any case. So what we're going to do today is we're going to use this motivation from the Nyquist sampling theorem, and we're going to go ahead and use that information to replace all of our functions with discrete versions of the functions. This is both a nice theoretical thing that we can do, but it also is a practical thing because we can't sample a continuum number of points, and we can only have a finite number of samples even in any other case. So what we're going to do then is we're going to go ahead and take a look at discrete versions of all of our different operators. This includes the Radon transform, this includes the Fourier transform, the back projection, convolution, and all that stuff. We're going to replace all of our different definitions with discrete versions of the same. And this is all motivated by the Nyquist theorem. So then using that, we can go ahead and start getting back to the much more practical issue of inversion from a discretely sampled sinogram. I'm getting increasingly blinded here. In any case, that's what we're going to do today. It's going to be a bit of a long lecture, putting together each one of these discrete versions of each of these operators and showing various properties about them and their interactions with things like convolution. Can I? Yeah. Anyway, let's move this back a little bit. There we go. I'm safe for another like 30 seconds. In any case, but yeah, so that's what we're going to do. So let's go ahead and get started, and yeah, I'll see you on the other side. Okay, so the whole theme, move this microphone a little bit better spot. The whole theme of the lecture today, sorry, several bumps and scratches. There we go. That sounds a little bit clearer. So the theme of today is to talk about discrete image reconstruction. And so this is basically going to be taking a look at a whole bunch of different discretized operators from the things that we've been talking about so far. So we need to develop some discrete. Am I spelling discrete right? Yeah, discrete. Oh my god. Discrete, low pass filters. we're going to talk about discrete Radon transforms, discrete Fourier transforms, and discrete back projection. And also discrete convolutions. And why discrete everything? Well, we can only talk about our data that we always get is not usually a continuous function. The idea is that we have some sort of, we're presuming that we have some sort of continuous function, right, in the world, but we can only have so many finite samples. We might have a lot of samples to the point where we don't even need to do any interpolation or guess about the things that come in the middle. But at the end of the day, we can only have a finite number of samples because, well, you can only get a finite number of samples with a finite number of sensors and a finite amount of time. And of course, computers can only store information discretely. So we live in this world of discrete sampling, and so we need to be able to sort of get an idea of how close we are to the actual continuous Fourier transforms that we're actually trying to work with. So to that end, that's what this is all going to be about. And to a large extent, we are relying on Nyquist theorem. And basically is saying this, where we have f of x is equal to the sum of n equals negative infinity to infinity of f of pi n over L of sine of Lx minus n pi divided by Lx minus n pi. And we know that this is equal to each other if Fourier transform of f has a compact support, i.e. f is band limited. So, and it has to be square integrable. But if you think of it as being, say, a band limited Schwarz space function, Schwarz space functions are always square integrable. So so that's basically where we're coming from, is that we're going to use this idea where instead of talking about a continuous number of points, we're going to just deal with this discrete collection of samples. Now this is the countable number of samples that we're constructing f out of, but since this decays to 0, earlier and earlier points here are going to be more strongly weighted than ones that are further and further apart at any given x. So yeah. Although the convergence is rather slow. Okay, so let's see. So what we're going to do then is the first thing that Feynman does, Timothy Feynman, out of his book. Sorry, it's just after lunch. The Mathematics of Medical Imaging. Is he takes a look at discrete low-pass filters. So we're going to follow him here. Okay. So generally speaking, we're going to have, so we have example. We're going to start with the Shep-Logan filter. And remember, this was given as a omega is equal to the norm of omega. All these filters that we're dealing with, because we're trying to relate them back to filtered back propagation or back projection, we're going to have this term in there, and then it's going to be some function times that, and then times some sort of windowed function. So this is times sine of pi omega divided by 2L divided by pi omega divided by 2L times the square wave of width L at omega, and he's kind enough to provide the definition again, and so I'll do that as well. So this basically, if you expand this definition, this is what you get. 2L for omega less than L and less than or equal to L, and 0 for all other values. Okay, so and so that's what we end up getting. Yeah. So then the idea is that we're going to try to go ahead and use the fact that A is band, well, not A is band limited, but since A has compact support, means that the inverse Fourier transform of A is band limited. So if we take the Fourier transform of this function, we get a function of compact support, so then therefore is band limited. And so then if we want to describe F inverse of A at X, then we know that this is going to be a sum n equals negative infinity to infinity of F inverse A at so pi n over L times sine of Lx minus n pi divided by, again, Lx minus n pi. Make sure should have had a parentheses here. There we go. So Lx minus n pi. All right. So that's what we can do. And so if we want, we can get this guy back exactly from this series, and so then we just need to figure out what this guy is here. And so we can replace this guy with its discrete samples and still be able to recover the entire function later if we want to get it back. So that's what we're going to do. So just picking through here, we're going to go ahead and actually compute F inverse of A at X, and yeah, so we'll go ahead and do that. So F inverse of A of X is equal to 1 over square root of 2 pi times the integral from 0 to L of 2L over pi sine of pi omega divided by 2L, and now usually we would have e to the I omega times x, but since we can take advantage of the fact that we can write this as cosine of x plus I sine of x, well, omega x. And then we can use symmetry properties to kill off one of these terms. And so at the end of the day, what we're left with is cosine of x times omega times d omega. Okay, so now how do you go ahead and integrate this is a question. So there's a few ways to go about it. A favorite is usually doing something like a product of sum formula. Which you can derive from the sum and sum of angles formulas, etc. And yeah, or you can do it directly from Euler's thing and just replace this with Euler's description of cosine, replace this with Euler's description of sine, and then you can go ahead and integrate it. It ultimately ends up being just an undergraduate exercise. And so these are the sort of things that Fima was doing as he put this together. So here we have L over pi squared. I think we're using a different normalization here. So so we have 1 over 2 pi here, and looks like 2 was absorbed So we're going to keep an L up here, and then we have another pi that's coming out. So that's what we get there. It's going to be cosine of x minus pi over 2L and this here times omega divided by x minus pi divided by 2L minus cosine of x plus pi divided by 2L times omega and divided by x plus pi divided by 2L. And then this guy evaluated at 0 and L. And so then at the end of the day, you can continue working this out, and you get L over root 2 times pi to 3 halves times, it's a mess, cosine of Lx minus pi over 2 divided by x minus pi divided by 2L minus cosine of Lx plus pi over 2 divided by x plus pi over 2L. And then we have some big brace, and then minus this term, 1 over x minus pi over 2L minus 1 over x plus pi over 2L. Okay, and so we have that. But at the end of the day, since we only needed f inverse of a at pi n divided by L, and I'll let you guys work this out, this ends up being 4L squared divided by pi to the 3 over 2 times pi times 1 minus 4n squared, and we have square root of 2 down here. And yeah, and so that's what this ended up being. It occurred to me that I think I actually wrote down the normal. I forgot normalization constant here. I'm pretty sure it should be like 1 over square root of 2 pi. Just look up in the last lecture, and that should take care of most of everything. Anyway, but yeah, that's the general idea. So then you can do the same sort of deal with the Bram-Lack filter. Which was also defined a few lectures ago. And so this one was AW, which is equal to norm of W, or omega, times square wave of width L times omega. And so this is just simply a sharp cutoff here. So we're not doing anything fancy. And so you can go ahead and do that. And ultimately what you end up with at the end of the day is modulo some normalization constant mix up pi n over L is equal to L squared divided by 2 pi times 2 times sine of pi n divided by pi n minus sine of pi n over 2 divided by pi n over 2 quantity squared. And so that would be what you get. But just avoiding it because this is going to be a long lecture, so I'm just trying to give you a general idea. You can go ahead and work that out yourself. And again, I think I'm off on this constant here because we've been jumping between two different versions of the Fourier transform, which only differ by a constant. So I mean, asymptotically, all these are the same, just like modulo some constant out in front. But yeah. So you can go and do that. And if you want to see the details, Feynman does a little bit more work here in discrete image reconstruction, but it's really just integrals straight out of calculus 2. So now let's talk about the discrete Radon transform. Okay, now and this is exactly what we were talking about earlier. So generally speaking, we have a subject, and then we have an emitter, and basically on this emitter we have several sensors that we have several emitters on this array, and then we have several receivers on the other end, right? Now, each one of these, this is a sort of a discrete array of samples that we get given each angle. But of course, we can only send an X-ray out at a given fixed number of angles, and so then we can basically have another array that's going off this way, and then that gives us another collection of discrete samples of the radon transform, or our sinogram. And so this in particular is what is called parallel beam geometry, and so all of these beams are going in the same exact direction, and yeah, so we only have a finite number of samples. So then we're going to be talking about what we've been getting out of, say, MATLAB is a discrete collection of points. And so here we had theta, and here we had t. MATLAB basically treats the middle point of here as 0, and so yeah, and that's what you get. And so yeah, so you just have to keep in mind that the information you're getting, you're going to be changing it at a discrete number of angles, and so these are rotated at some fixed rotation, say pi over n, and so then you have basically your total angles are going to be this, and so it's going to be k pi divided by n, going from 0 less than or equal to k less than or equal to n minus 1. And yeah, and then on each of these we have some sort of sample spacing along here, and so it's going to be some sort of tau bigger than 0, and yeah, so we're going to be given some sort of samples that happen at t values of j times tau, and going from -m less than or equal to j less than or equal to m, and this gives us, say, 2m plus 1 samples, for instance. So these are our t's, and this is our thetas. And so altogether, if you take a look at for each of these j's and k's, we end up having what we call a discrete radon transform of fi at fjk, and this is going to be specifically the samples of the radon transform, like so. Here. So the idea is that each one of these we're assuming is going to give us some sort of like true radon transform when we compare the difference between the receiver and the emitter, and of course this is also assuming Beer's law, but you have to make some assumptions somewhere. So we'll assume that we're getting a proper radon transform all the way through, and so then but then we can only get a finite number of them. So we're assuming perfect information, and these are our samples. And of course, in reality, you get signal noise and other things like that. So there might be extra cleaning that you have to do to your data. But yeah, this is what we got. So thus far we've talked about a discrete low-pass filter and a discrete radon transform. Now we know that basically what we're looking at is f of xy is approximately 1/2 of the back projection of the inverse Fourier transform of a lower pass filter convolved with the radon transform of f, right, at xy. And so, sorry, I keep hitting this thing. Anyway, I'm trying to bring the microphone closer so you can hear me more clearly, because I noticed before in a couple other videos that it was kind of echoey. Still getting used to this thing, but I also have a pop filter right in front of it, so it sits right where my pencil keeps whacking. So, in any case, so here we have a discrete version of this,
and we have a discrete version of this. And so that if we can just figure out what the heck convolution is and how to do a back projection with these two discrete quantities, then we could actually invert f. And then more broadly, we would like to talk about things like the discrete Fourier transform, and because that is sort of the theme of this class, is a Fourier transform, and that will lead us to what is called the FFT. I'm not sure how deep I'm going to go into the FFT algorithm. For the most part, FFT algorithms are already implemented in everything we care about, and it gives you a DFT at the end of the day. It's just a really fast way of doing it. And so I might give a high-level explanation of what the FFT is, just to save us a little bit of time. But we'll see when we get there. But okay, so that's where we're at now. So basically what we're going to do is we're going to define discrete convolution, and then we're going to try to define a discrete back projection, and then we'll actually have a method of doing reconstruction from samples. So yeah, that's pretty happy.
Okay, so we can go ahead and get started in our journey through Feynman's book, and right now we are in Chapter 8, Section 5, and this is the section he titled Discrete Functions and Convolution. So just like what we said before, we are making a shift from thinking of continuous functions and using the Nyquist theorem as justification for shifting to talking about functions over a discrete set of points. So basically, before we had R to R, and now we're replacing this with f going from, say, z to r, and we make this replacement like this. So basically, we're just looking at f of minus 2, f of minus 1, f of 0, etc. And we'll just write this as f minus 2, f minus 1, f of 0. We might also use the arguments that would come out of the Nyquist theorem. And we know that if we use just these points and the function is band limited, we can always reconstruct it. So this is encouraging us, along with all the things we've just talked about, to doing this. I'm also just shifted recording out in my backyard, so we have a nice ambiance of things. And we also have my tree dropping acorns on me. So if you hear a big bang and I forget to edit it out, I apologize. So to start off in the section with his convolution idea is this. So we're going to so his definition of a discrete convolution, and this coincides with a regular convolution. And in fact, if you know any measure theory, the previous convolution that we had worked with is really just basically an integral against Lebesgue measure. So now you could get this exact same definition if you replace Lebesgue measure with just, say, a collection of delta functions. So I'll go ahead and give the definition here of the discrete convolution, and I'll give the next proposition, but really the proof is exactly the same as before, and in fact it is subsumed if you take the measure theory perspective. So let's go ahead and get started with this. So we're basically going to let f and g be discrete functions. So functions over z mapping to r, or even c. We could put c there if we'd like. It might be more appropriate with the fact that we're talking about Fourier transforms. And so then the discrete convolution of f and g, given as, say, f star bar g is equal to the sum, j going from negative infinity to infinity, of f sub j star with g of m minus j, for
each m in Z. And so should have a sub m there. Okay, so the idea is the convolution gives you another discrete function, and this discrete function can be determined by taking a look at the series. Now you notice that the series, if we replace the integral here, and instead of just these discrete functions, we have fj m minus j, then that would basically be what we had before. You say just y here for j and x here for otherwise, and then ta-da, that's a regular convolution. So because of that, the next proposition is going to follow immediately. And so we can go ahead and just state this more or less without proof because we've already proven it. So proposition, we have that the discrete convolution is commutative, so you get the same function out of it, whether or not you start with g or f. It is distributive, so f star bar g plus h, it's equal to f star bar g plus f star bar h, convolve if you want. And then the third one is the linearity property. It finishes this linearity property, so you can pull out scalars. So alpha g is equal to alpha f star bar g. Okay, so between these two, we get linearity in both variables, and yeah, there we go. And I think associativity works, even though he didn't mention it in the property in the proposition. So alright, so that's good. Now, Feynman also wants to talk about sort of periodic discrete functions. And the reason why is that basically we can only sample a function at a finite number of points. I mean, the Nyquist Theorem and all these other things that we're talking about actually samples at a countable number of points, and even then, I mean, it's better than a continuum, but it's still not feasible to work with. So we're always going to have like a finite number of samples. And so there's two ways that you can really extend from, I mean, there's a lot of ways you can extend from a finite number of samples, but two main ways that you can consider is, one, you can do zero padding. So you can have, say you have samples at f1, f2, f3, etc., up to fn, and then you can just say, well, I'll just assume that that's all the information. All right, so you can say, just put zeros everywhere else. So zero padding. But another thing you can do is you can go ahead and assume that the function is periodic. And so so basically what we're going to do is we're going to use the sample values, say f1, f2, all the way up to fn, or well, up to fn minus 1, and we'll assume that f of m plus f of m is equal to f of m plus n times n, right? And so then that means that if we want to define so then basically we just assume that we're going to end up having a periodic function from here on. And so that gives us another definition of convolution that only uses these values. So we say that for two n periodic functions, where we have, say, f is defined through the sequence f sub k for 0 less than or equal to k less than or equal to n minus 1, and g, hold on,
There's really no quiet place in this world. Anyway, so then we have g, k is 0 less than or equal to k less than or equal to n minus 1 as well. Then what we have, so noisy. Then we define the discrete convolution. Is defined as, so we have f star bar g sub m is equal to the sum j equals 0 to n minus 1 f sub j g of m minus j for each m and z. Okay, so the difference between this and the previous one is that the previous one actually ends up having an infinite sum, by infinite sum, and this one is only a finite sum. Consequently, for periodic functions, discrete functions, f star bar g is periodic itself. And that's not really that much of a surprise. Keep in mind also, we can't define the discrete convolution on functions that are periodic, because that means that these samples aren't going to be decaying, which means that this sum isn't necessarily going to be decaying either. And so the terms in that sum are going to be decaying, so that means the internal sums aren't going to 0, and so then therefore this series would not exist for discrete convolution. So we do have to restrict it to this finite set. Alright, so now Feynman introduces this proposition. This is 8.11 in his book, and here he connects the ideas of the bi-infinite functions and the periodic ones. And so let's go ahead and look at this definition, at this theorem statement. So we're going to go ahead and let f and g be two-way infinite discrete functions. All right, so this just means that it's a function over with domain z, and suppose there's some natural number k for which gk is 0 for all larger indexes. So, and suppose there exists a k in n so big K, and then such that g sub k is equal to 0 whenever k is either negative or k is bigger than big K. So now we're going to let m be an integer that is bigger than, say, k minus 1, big K. And we're going to let f and g tilde on each be 2m plus 1 periodic functions. The discrete. Okay, and we define them this way. So f tilde sub m is equal to f sub m, and g tilde of m is equal to g of m. Here, Feynman is just adopting the, getting rid of the subscript there. He seems to be mixing it up a lot here. Alright, so for negative m is less than m and less than or equal to big M. Okay, so it's a big hypothesis here, but basically what we're saying is that, say G vanishes outside of some region and it's all the negative terms are 0. And then if we replace these guys with some sort of like a version of a, if we take these points of G and then we extend G periodically, then what we can do is we can go ahead and we get this theorem, which basically says that we have this. So thus then we have f convolved with G of m, and this is the sort of bi-infinite version of the convolution, is equal to the periodic version here evaluated at m, and this is true for 0 is less than or equal to little m, less than or equal to k minus 1. Okay, so we have agreement here with these convolutions. I don't think the animals like me being out here. Anyway, yeah. Okay, so then what we're going to do next is we're going to go ahead and prove that, and I think I'll probably just move indoors. It's going to be a bit much. All right, so you won't see a difference. Well, you'll hear a difference, but I'll continue this lecture myself in a few minutes. Okay, so let's go ahead and jump into this proof. So let's see. So basically, start proof. The proof is pretty simple. Just following Feynman, we're going to let f, g, k, m, f tilde, and g tilde be as stated. And so it's kind of a long hypothesis. So we are saying that this guy is a 2m plus 1 periodic function that matches f at those particular points. And again, same with g tilde. And we know that g vanishes for indexes bigger than big K and all negative indexes. And so, so I think that's good. All right, so then, so for M and J, satisfying this inequality, so 0 is less than or equal to M, and J is less than K minus 1. We have that the absolute value of M minus J is less than or equal to K minus 1. Now we want this because this M minus J term is going to be coming up in our convolution, and so then we'll know that we're sort of sitting within this realm as long as we're sticking with positive M and letting J range between say 0 and K minus 1, or well, at least just less than K minus 1. See. Oh. Yeah, sorry, I misread that. Both of these have to be within 0 and K minus 1, obviously. Okay, so then, we just go ahead and carry this out. So we take our two bi-infinite sequences, f and g, and take their discrete convolution and look at index m. Expanding the definition, we have j going from minus infinity to infinity of f of m minus j times gj, right? Or sub-indexes or whatever you want. Okay, and so what do we know? Well, we know that gj vanishes for all negative indexes, and we know it vanishes at any time we are bigger than, say, was it bigger than k minus 1 or bigger than k? Okay, bigger than k. Or, well, sorry, bigger than equal to k, that's what that should be. And so, then we can switch it to this. So we can say this is the sum
going from j equals 0 to k minus 1 of f of m minus j times gj, right? With no change to the series, because otherwise everything was just 0 anyway. Okay, now continuing, we can go ahead and replace k with its periodic counterpart, m minus j, because m minus j is less than k minus 1 in absolute value, and so then that means that, basically we can replace f with its periodic thing, because they agree. Okay, and then what we can do with gj is we'll leave it alone for this time, but next round we can go ahead and replace it. So we have the sum j equals 0 to k minus 1 f tilde of m minus j, and here, instead of stopping at k minus 1, we'll go from going from m minus m to capital M, just using this periodicity we established. Sorry for the bump. And then we get g tilde of j, right? So then they agree. So we just look at, so basically what we're saying is that we're picking some m bigger than k minus 1, and then we are taking these two guys to be the m periodic functions, the 2m plus 1 periodic functions, right? And so since we know that gj actually vanishes for most of these points, we can just sort of add that back in for gj and tilde and etc. Anyway, so at the end of the day, this is the same as f tilde star bar g tilde sub m, where this is the periodic convolution, and this is the discrete convolution. Right, so we're done. Okay, so basically the discussion that Feynman has after this is talking about this concept of zero padding. So the idea is that you have some sort of sequence coming from G, but you only have a finite number of points of it. So you have some function that you care about, but you only have, say, maybe these samples, but you still want to do basic operations like convolution and things like that for signal processing. And so what this basically says is, if we do some zero padding and just add on some zeros to our sequence, and then we take a look at it, another function that we want to take convolution with, then the zero padded version of G will agree with the regular convolution, for some restricted set of values. And so so in that way we can go ahead and trust a lot of the values that we got out of the convolution from a discrete number of samples, at least at a finite number of indexes m. And so that's sort of the whole idea of that theorem. And he has an illustration in here where he takes a look at the function the square wave at 1/2, and he's particular about the definition here, where he says that you take 1 if 1/2 is less than or equal, negative 1/2 is less than or equal to x, and we put the equality on the other side, so 0, and so it's going to be 0 otherwise. So so if we take a look at this axis, just see what he's talking about. We put, say, minus 1/2 here, and we put positive 1/2 here, and we take a look. Basically, this is what we get. So his intention is to force this guy to be 0 at this endpoint, and 1 at this endpoint. Okay, and so so then his example, he says basically we're going to sample pi at 1/2 at the points x equals negative 1/2 and x equals 0, and so then he gets this sort of, and he generates a 2 periodic function. F, which basically is defined as F0 equals 1 and F1 is equal to 1. And then if you just take a look at the convolution with itself, discrete convolution with itself, at say 2 points, so at 0, so we get f at say 0 minus well, I guess I don't need the sum there. So we have f of 0 minus 0 times f of 0 plus f at -1 times f at 1. Then what do we end up getting? Well, we get 1 plus 0 times 1, which is equal to just 1, right? And if you take a look at f star bar at 1, then you get f at 1 minus 0 times f of 0 plus f at 0 times f at 1, right? And so this is going to be 0 times 1, or sorry, make sure I'm doing all this right. So f of 1 minus 1 times f of 1, right? Okay. And so at this guy, it's going to be f of 1, and so that's going to be 1 times, well, yeah, f of 1 times 1 plus 1 times 1, right? This gives me 2, right? Did I do that right? I think I might have messed up this one. Not getting exactly what Feynman had here. He got 2 for both of them. It's bothersome. I think I'm right though. Just double check something. Yeah, I think. Yeah, okay. It doesn't agree with what Feynman says, but I'm pretty sure I'm right on this. He doesn't actually spell out exactly what he was doing. But yeah, as far as the convolution definition goes, I mean, there's not really much to it. I don't know, maybe if you see something, you can speak up, but this seems to be right to me. Right, so then what we can do instead is that we can actually pad, so now let's pad f with 2 zeros to make it a 4 periodic function. And so then, so basically what we're going to say is that, f, we're going to place with f tilde, and it's going to be 1, 1, 0, 0. Although you could also think of it as sampling the function here, actually, here and here and here and here and here. So it actually sort of agrees with the function anyway. But yeah, but then if you take a look at f star tilde bar f tilde and look at, say, 0 to start with, so we're gonna get, so then what we end up getting is this. We're gonna have, say, f at f tilde, looking at that entry that goes in 0 minus 0, f tilde 0, plus f tilde at 0 minus 1, f tilde at 1, plus f tilde at 0 minus 2, f tilde at 2, plus f 0 minus 3, f tilde at 3. And so then what we end up getting
is this. Yep, alright, so I'm agreeing with this agreement again. So 1 plus 0 plus 0 plus 0 equals 1. I'm just losing confidence here because of that first hiccup, but it looks like otherwise I'm right. F tilde times F tilde at 1, which is F of 1 minus 0, F 0 plus F of 1 minus 1 times F of 1 plus F at 1 minus 1. 1 minus 2 times F of 2 plus F of 1 minus 3 times F of 3, and put tildes everywhere. Okay, and then what do we get? So this is going to give us 1, this gives us 1, this gives us 0 plus 0, so this gives us 2, and then we get F tilde times F tilde at 2, and ultimately, just following what Feynman does, we get 1 times 0 plus 1 times 1 plus 0 times 1 plus 0 times 1, and that equals 1. And finally, we get F star F at 3, which just gives us 0. So the convolution then is basically at, say, so at 0, 1, 2, 3, where we end up getting is we're at 1 at 0, at 1 we're at 2, so 1, 2, and then at 2 we are at 1 again, and at 3 we're at 0. Right, so we get something that looks like this. And if we go ahead and we take a look at what the actual convolution is, this is something that you can just work out yourself. By 1/2 star with 1/2, it actually is equal to 2 times 1 minus absolute value of x, which is agreement with these discrete values. So that gives you some confidence that the zero padding actually ends up giving you something incredible that ends up extending. So yeah. So now what we wanted to move on to next is talking about the discrete Fourier transform. We're just putting these one together at a time so we can finally talk about discrete image reconstruction. Okay, and I guess I'll switch to blue. All right. So in order to actually end up using this in applications, we're going to end up talking about the convolution. The convolution in for functions in polar coordinates is taken with respect to the radial variable. Okay, and so the whole idea here is that the basically we're going to be writing this at some point. So we have f inverse of a, which is probably going to be one of our low-pass filters, and then we have the discrete Radon transform hanging out in here. If we're looking at this at m comma theta, this is constant with respect to this is convolution isn't with respect to theta. So so this is sum j equals 0 to n minus 1, and then we'd have the inverse Fourier transform of low-pass filter sub j at the discrete Radon transform of f at m minus j comma theta, right? So this is more or less what we're going to be talking about. But now we just need something to put in place of this guy, these Radon, the Fourier transform. So let's go ahead and start talking about it. So we had the discrete Fourier transform. Okay, so if you remember, we have
the Fourier transform for our regular functions, and so for us, it's a little bit different than what we see in Feynman's book. It's going to be 1 over square root of 2 pi times the integral from negative infinity to infinity of f of x times e to the minus I omega x dx. Basically, the difference between what we do and what he does is it comes down to his normalization constant, but otherwise everything agrees. And so basically what we're going to be doing is we're going to be replacing, for a discrete function, we're going to be replacing the integral with a sum, and then omega is going to be replaced with sort of integer multiples of omega. Or x is going to be replaced with k, more or less. So basically, if we take a let f be a discrete periodic function with period n, and then basically what we will define is the discrete Fourier transform. And so we define the discrete Fourier transform of f as this. So it's going to be f, and I'll put a d on the bottom to say it's discrete. So j, and this is going to be the sum of k equals 0 to n minus 1 of f, so k e to the minus I 2 pi k j divided by n. And here we're letting this be defined for j equals 0, 1 up to n minus 1. Although you should note that since the exponential function itself is periodic, and e to the I 2 pi basically gives it periods of 1, this discrete Fourier transform itself is a periodic discrete function. And so then we say and so for j bigger than or equal to n, f d f, so j is extended periodically with period n. So basically that's definition. So basically, if we have a n periodic function, then this Fourier transform ends up being an n periodic function as well. So let's see. There's a couple examples in here, and we'll do some examples in MATLAB later, and so I'm not going to jump into this too much, and we do kind of want to get through the lecture, and so in some reasonable time. I don't want you to be here for like 3 hours. So then together with this discrete Fourier transform, we naturally want to be able to map to and from periodic functions. So to and from the Fourier transform and the original function itself. And so what's nice is that since we have an n periodic function coming out of the Fourier transform, we know we can just map to another n periodic function through the inverse transform. And the inverse transform is more or less what you would think, just like with the inverse Fourier transform for continuous functions. We just flip sign, and that's more or less what we do here. So so here we have for an n periodic discrete function, and we'll say g, the discrete inverse Fourier transform of G is the n periodic function defined by this. So we have the inverse Fourier transform of G sub n is equal to 1 over n times the sum k equals 0 to n minus 1 of gk e to the I 2 pi n divided by n. And again, this is defined for n going from 0 up to n minus 1, and afterwards it is extended periodically. And so then this results in the theorem, and basically it says this: for a discrete function f with period n, we have what you would expect, or what you would hope for. We have the discrete inverse Fourier transform applied to the discrete Fourier transform of this periodic data f sub n is equal to f sub n for all I n z. So that's a pretty strong and remarkable statement. And so in order to prove this, we're going to have to demonstrate a couple things about the exponential function. So we're going to start with this lemma, and so basically we have this for any non-zero integers, say n and m, we have this: the sum of k goes from 0 to n minus 1 of e to the I 2 pi mk divided by n. This should be equal to n if m over n is an integer, and 0 otherwise. So that's pretty handy. So feels a little bit like a number theory thing, but it's not really too bad. So basically, proof: if m over n is an integer, then basically we have e to the I 2 pi k times some integer. We'll call this pick your favorite integer, s times s, and basically this is equal to 1 for all k, and that's because basically k is going to land exactly on these periods each time, and so hence that means that the sum k goes from 0 to n minus 1 of e to the I 2 pi of k times s is equal to the sum of k equals 0 to n minus 1 of just ones, and so that is just n. So just a check. And if it's not, then this is a little bit more interesting. So basically, if m over n is not an integer, then we have that e to the I 2 pi m over n raised to the nth power minus 1 is actually equal to 0. How do we know that? Well, you just move the n aside and they cancel, and that gives you e to the I 2 pi m, and that's just 1. So so there you go. But what we do know, but e to the I 2 pi m over n itself is not equal to 1. And we know that just because m over n is not an integer, and so there's only one point on this period where that is actually, where this guy ends up being just identically 1. I mean, it's running around on the unit circle, right? And so it's only going to be 1 here, right? And so this is going to be, maybe I should draw this bigger. So basically you have this function here, and e to the it basically runs over this, and so and this is going to be 1. This is going to be I. This is going to be -1, and this is -I. And so at integer values, e to the I 2 pi times k is going to be there. And so, and otherwise it's going to be elsewhere on this, and so not 1. Okay. Then you can take a look at the cyclotomic polynomial. Consider, say, x to the n minus 1, and just from pre-calculus we get this, x to the n minus 1 factors like this. So you x minus 1 times x to the n minus 1 plus x to the n minus 2 plus all the way down to x plus 1, and so then since so then if we plug in e to the I 2 pi m over n is equal to x, we know that this is not 0. And so just by the algebraic properties, sorry, not algebraic properties, but the fact that this is what we call an integral domain, this is 0. So we know that polynomials over a complex field forms an integral domain, and so then this follows. But if we plug this in, e to the I 2 pi m over n, basically this is going to be this. Basically, that's what the summit ends up being. And so since this is 0, that is 0, and done. Okay. So cyclotomic polynomials are often very useful. I've seen them come up with a bunch of number theory but also in analysis, and so they're a handy tool that comes up sort of randomly. Yeah. So now what we're going to do then is we're going to prove the inversion theorem. All right, so this is actually a really straightforward proof given what we've just shown. So basically what we're going to do is we're going to let n be an integer such that it lives within sort of the period of our discrete Fourier transform. So we know that that we're mapping n periodic Fourier n periodic discrete functions to other n-periodic discrete functions through the Fourier transform and also through the inverse Fourier transform. So then we know that if we can show that the inversion formula works for this finite number of points, then we have everything we need, and it follows out. The proof actually falls out just like what we see for the regular Fourier inversion theorem, where it's really just an exchange of integrals, and here it's an exchange of sums. So basically we have the inverse discrete Fourier transform applied to the discrete Fourier transform of f, and looking at this at the nth index. And so this is going to be 1 over n times the sum k equals 0 to n minus 1 of the discrete Fourier transform of f, so k, and times e to the I 2 pi k n divided by n, right? And this is just following the definition. And so then what we do next is we expand the definition of the discrete Fourier transform on the inside, and so it's going to be a sum k equals 0 to n minus 1 of the sum. We're going to switch to index m, it goes from 0 to n minus 1, of f sub m. So now we're back to the original sequence there. Times e to the minus I 2 pi mk divided by n. Okay. And then this again times e to the I 2 pi k n divided by n. All right, so now the only thing you could ever do here to get anything meaningful out of the problems like this is to exchange the order of summation. And there's nothing tricky about this one. Since they're both finite sums, the whole sum is finite, so you're allowed to do anything you want. And so this is a 1 over n times the sum m equals 0 to n minus 1. And then here we're going to have fm times the sum of k equals 0 to n minus 1 of e to the I 2 pi n minus m k divided by n. Okay, so what we've done is we've swapped the order of summation, so we swap those two guys, and then once we swap the order of summation, the k f doesn't depend on k, so we can go ahead and just factor that out, right? And then everything that's left are these two these two exponentials, and we can combine them, and basically it just ends up being n minus m. So then this leaves us two cases. If m is equal to n, then the e to the I 2 pi n minus m to the k over n is equal to 1 for all k, because it's just identically 0. And so the sum, and so then the sum on the inside is equal to n. And if m is not equal to n, then by the theorem, and by the lemma preceding, the sum on the inside is 0. Right, so then that basically leaves the only thing that survives out of this entire summation is when m is equal to n, and so thus we have f sub d inverse of f sub d of f is equal to 1 over n times fn, the only survivor, times capital N, and so that is equal to fn. And so then by this periodicity argument, we must be done. So pretty straightforward. Right. So the next thing we want to talk about then is finally combining this convolution idea with the discrete Fourier transform. And so this is what we get. So for two discrete functions, f, which goes from f sub k, 0 less than k less or equal to n minus 1, and g being equal to gk, 0 less or equal to k less or equal to n minus 1 with the same period n. And if one doesn't have, and in practice, if one doesn't have period n, the other one does. I mean, that's where the zero padding comes in. And so basically we have the following, that the discrete Fourier transform of f star bar with g is equal to f d of f dotted with f d of g, right? And so so then just like before, the discrete Fourier transform of the discrete convolution is the product of the discrete Fourier transforms, right? So this is again that sort of algebraic preservation that we wanted. Okay, so let's go ahead and prove this. Okay, so what we start with is the discrete Fourier transform of f, and looking at the nth index, and basically we want to show that this matches the nth index of the other side. Okay, so this is what we have. First thing we do is we just go ahead and expand the definition. So we have the sum k equals 0 to n minus 1 of f, so k e to the minus 2 pi I n k divided by n. And this times the sum k equals 0 to, or well, they use index L, n minus 1 of g L times e to the minus 2 pi I n L over n. And honestly, this proof works out more or less as it does in the continuous time case, except for like one little caveat, and that is this leveraging of the periodicity of g. And so sum k equals 0 to n minus 1 f sub k e to the minus 2 pi I n k over n. That stays the same. But now we're actually going to shift this other one by k units. So we're going to go from n minus 1, and we're going to subtract k off of that. So we get this sum, and L starts at minus k. But g is periodic, so it's going to be at L, and then we have e to the minus 2 pi I n L divided by n. And yeah, so then this times e to the minus 2 pi I n k divided by n. And now we go ahead and do shifting so we can get the convolution back. This guy stays the same. And so here now we have the sum of j going from 0 up to n minus 1 of g j minus k e to the minus 2 pi I n j minus k divided by n. These tiny indexes get annoying. And then e to the minus 2 pi I n k divided by n. And so here we're letting j equal k plus l. Okay, so then what we do is we move f sub k onto the inside, and you'll notice that the exponentials actually end up annihilating each other, or at least the k piece. So this and this end up killing each other, and then what we get is this. So we have the sum of the sum, and here we are going to have j going from 0 to n minus 1, exchanging the sums as we go. K equals 0 to n minus 1 of f sub k times g of j minus k, and then we're left with e to the minus 2 pi I n index j divided by n. Okay. But if we take a closer look, we see that this guy doesn't actually depend on k, so we can extend this out like that and factor out the exponential. And then this guy is precisely f star bar times g. And so that means that this is the discrete Fourier transform of f convolved with g sub n. And there we go. Okay, so that's proof. Okay, now to wrap up the discussion of the Fourier transform, I just took a screenshot of the Feynman book. So this is Tim Feynman's mathematics of medical imaging, and so this is his wrap up of the discussion. He hasn't proved these things, and but more or less it is straightforward to talk about. So here this is sort of the opposite of what we just proved, right? So before we were taking the Fourier transform of a convolution, but now if we talk about the Fourier transform of a product, we can sort of write this as the as a convolution of two different functions, and so this is more or less you can get at this by doing the same exact procedure, but using the inverse Fourier transform in the last theorem here. And as far as conjugation, if you take the Fourier transform of the conjugate, what you get is the conjugate of the Fourier transform, but in the opposite order. And then there's a Rayleigh-Plancherel theorem here, which relates the square norm to the square norm for n periodic function, and this is where we have a period n. So basically the power of this discrete sequence is proportional to the power of the Fourier transform of itself. Okay, so with that wraps up the discussion of discrete Fourier transform. And now there's one last discrete transform that we should really talk about, and that's the discrete back projection. And so this is going to be the last thing that we need to work out before we can go ahead and actually do everything that we want to do. So let's go ahead and talk about it. So if you recall, the regular back projection, it applied to a function h at xy is equal to 1 over pi times the integral from 0 to pi of h of x times cosine of theta plus y sine of theta comma theta d theta, right? And so basically what we're going to do is we're going to replace theta with discrete increments. I don't know if you can read that, but basically we're going to have a set of the angles k pi divided by n, and this is running from 0 less than k less than n minus 1. Right. So then what we ultimately get is the discrete back projection of h of xy is equal to 1 over n times the sum k equals 0 to n minus 1 of h of x cosine of k pi divided by n plus y times sine of k pi divided by n and comma k pi over n. So it's more or less what you would expect here, but just doing it like this. Just replacing theta with these values here and summing over all of them. And so the d theta here became just the difference between consecutive terms, which would be pi over n. So that pi cancels with this, and it leaves 1 over n here. So this does leave us with a bit of a conundrum. So it turns out that the data that we're going to end up getting out of this system is not going to line up exactly with these discrete points. And so so basically, if we take a look at this, and we were running k going from 0 to n minus 1, so we're running this from 0 to pi, and we're taking a look at our sinogram, right? If we pick let's pick some nice cogent numbers. So I'm going to pick, x being cosine, x being, so I'm going to take a look at 1, 0 for our xy, right? So what ends up happening is you end up going from, say, t equals 1, we'll call this t0, and so say this is theta 0, and on over here we'll just say this is t equals minus 1. So we know that we're going to get something like this, right? Or well, actually, we're going to get something like this, right? So this is cosine. Now, each of these are only sampled at a finite number of values, and so cosine isn't always going to land right at one of the points that you care about. So you might know the values at these points, say here and here, but what you actually get when you compute, x, so taking a look at, say, cosine of k pi over n, well, let's put that in a different color, say red. So you get cosine k pi over n. It's going to get you here, but the values that we have are actually here and here, right? And so, the use of the back projection, the discrete back projection, requires interpolation. And there's a large number of different interpolation schemes that you can go with. You can do, interpolation with, say, polynomials. You can do it with splines or kernels, or or just keep it really, really simple and just do linear interpolation, or even just force it to be one or the other at the endpoints. But whatever you need to do, you're going to get sort of different kinds of error bounds that will end up coming out of this. And so we'll try to see if we can work in different explorations of this sort of idea. And if you look at Chapter 8, there's a whole section here on interpolation. I actually have a number of lectures on polynomial interpolation and also kernel interpolation, if you want to go ahead and take a look at those. And that covers most of what's in here. And so if you have a little bit of extra time and you want to see how interpolation theory works and how these things come together, you can take a look at that. And Feynman doesn't really go into the error bounds at all in here, and so and in my lectures I do. But yeah. In any case, so this is a good spot to stop, and then next time, and then we'll talk a little bit about some other properties of the Fourier transform, and then we'll get to proper discrete image reconstruction next. All right, thanks for hanging in there with me. There's a whole bunch of little random things, and there's a combination of just definition after definition after definition, and just proving things we've kind of already seen. And so but now we've finally built up to the point where we can properly talk about image reconstruction, and so now we're going to really change gears here and take a look at using this filter back projection and all these different low-pass filters to do image reconstruction, and then following that we'll talk about cache mark methods and algebraic reconstruction techniques, and then after that we'll have basically covered the basics of medical imaging, and we're leaving out some things like things like the fan beam geometry and stuff like that, and I can bring that up a little bit later, but the general principles are all the same. And so then after that we can go in and talk about some tomographic methods that come up in dynamical systems theory, and flow fields and other things like that. And if I can find ways to squeeze in it, we can talk about some in geology as well. But first, we're going to come back and do some image reconstruction, take a look at some proper sinograms. I'll see if I can track down some nice open source CT scans and things like that. And yeah. But yeah, for now, I'll check out, and we'll go to the closing.
Okay, welcome back. So now we have discrete versions of all of our different operators, and yeah, that basically leads us into doing actual inversion from sinograms and things like that. Ultimately, we're going to want to use a particular algorithm for computing the discrete Fourier transform, and that's going to be the Fft. And so the second project that I'm going to give you guys is going to be a combination of doing a sort of a naive approach to all of these operations, and then comparing it with sort of the sharper, smarter way of doing it. Okay, I think that's a good place to stop, and thank you for listening. All right, take care.